Please go ahead and start with.
Thank you.
Thank you.
Thank you for the opportunity to present here. It's a real privilege and an honor. I'll try to keep you entertained. I don't have too much to see, as you see, so please chip in anytime, ask, comment. I want to tell you about the problem of approach to introduce external data in a clinical trial. So here's the problem. This left block, these are the patients in a single-arm treatment-only study. On the horizontal axis are some 40-something patients. On the vertical axis, 10 covariates. This is a glioblastoma study, brain cancer. And for a variety of reasons, they set it up as a treatment-only study. This was going on in MD Anderson neuro-oncology department, so they treat these kind of patients all the time. So they have lots of historical data on similar patients. Wouldn't it be nice if we could use all these historical data, all these external data, and construct a synthetic control arm to add to the treatment arm from the current trial? Of course, in doing so, we have to be careful to make sure that these are comparable patient populations, because patient populations shift over time, standard of care shifts over time. So we have to do something to adjust it. And here's our approach, like a little stylized cartoon on the right-hand side. And it's actually very simple. What we do is we fit the red mixture model to the current data. Like the red mixture of normals is fit to the current data. We fit the green mixture model to the external data. Obviously, the picture is just a cartoon because, did you notice my data is 10 covariates, and they're actually categorical. Most of them are binary, some are trinary. For the sake of the cartoon, let's assume it's just univariate continuous. So we just have now the green mixture model for the external data, the red mixture model for the current treatment-only data. At that moment, it should seem plausible, although it's not obvious, but it should seem plausible that fitting these two mixtures, there's a special drift to the two mixture models. Do you notice these are synchronized mixtures? They share the same components. Or if you think of it as a mixture of some kernel with respect to some mixing measure on the center, then they share the same atoms for the centers. So it's like two synchronized common atoms mixture models, in which case it seems plausible now. An easy way to adjust the green data to start to look like the red data is drop that term, drop patients in that cluster, maybe downweight those patients, maybe upweight those a little bit, and it starts to look the same, right? That's exactly what we shall do. Bummer, I gave away everything in the first slide, yeah? All what I'll do now for the rest of this talk, I'll talk you through all the gory details, but I think most of you can already intuit what's going to happen.
Is that a covariate on the bottom or the outer?
Yes, it's the covariate, thank you. Here on the vertical axis are like the patient baseline covariates, stylized here as the just the real line.
The outcome is not part of this.
Correct. We hope that the two populations are not identical in the outcome, lest the new treatment would be a flop again. But it's actually a good observation. Watch me, like for the first 23 slides, I shall not talk about outcomes at all. Not slight, I'm exaggerating, yeah? But the whole game of making the populations comparable, making the populations match, happens on the basis of the baseline covariates. You don't want to make them match on the outcome, lest it's a foregone conclusion that you get a flop, right? This is joint work with Müller Chandra, who is at UT Dallas, Abra Saka, my colleague at UT, Ying Yuan at UTMD Anderson, and John de Groot is at UC San Francisco. Funny thing is, a couple of us were at MD Anderson at some time, yeah?
Peter, do you assume that all the X variables are continuous?
Does your method allow categorical experiments?
Quick answer, in the application, actually, all of them are binary only, sorry, categorical. For the cartoon here, I assumed continuous, yeah, to make life easier. What we really do is we use a probit model, and then once you have the probit scores, you're back to it's reduced to the same problem, yeah?
Okay.
But good observation. If anybody cares, we are waiting copies of the slides you could download from there. Like University of Michigan. What's the improved acronym? UM or UMix would sound much better, right?
We don't need.
Well, all that's coming up now is the details. This is again the current treatment only cohort. I'll try to consistently denote mark it with a red T for treatment. This is the external data, in our case, historical data. It's actually a very clean application of external data because it's external data in the sense of its historical studies. But historical studies in the same department by the same group of clinicians in the same place, etc. There's still no guarantee that it looks the same. And what we really have to do is we have to understand how they are different and account or adjust for those differences. There is an ongoing debate about the practice of setting up early phase trials in glioblastoma. The treatment only, and it's one of the references to talk about that. One issue is simply the number of patients whom you can recruit, even at MD Anderson, which is one of the largest cancer hospitals anywhere. You don't get those many for these trials. So the aim is to create a model-based adjustment that makes the blue population look like the red population so that we can proceed. And we want to do so allowing for missing data. In this particular case, there was like one biomarker that was not collected in earlier trials. We still want to be able to use that data. And it will be a nice little side comment when we get to it. We don't necessarily have to make them strictly equivalent populations. Introducing weights so that we can adjust for the difference is just as good. So we could relax the requirement to making them equivalent. We're obviously not the first ones to do that. In a way, actually, combining information across different data sources is a perfect application of Bayesian inference. It's like one of the big strengths of Bayesian inference, setting up hierarchical models to combine information across multiple data sets. The most principled way to proceed, or I think of it as kind of the canonical way to use external data in Bayesian inference, is to set up informative priors. And that's exactly what is done with historical data priors. One of the earlier ones being power priors, that's Joe Ibrahim and Ming-Hui Chen and others. What they simply do is you take the likelihood function from the historical data, use some appropriate fractional power of it, and call that your prior. The fractional power happens for the notion of information discounting, inflating uncertainty. Brian Hobbs and others have a variation to that, where they actually allow for a positive probability of the population not being exchangeable. So they introduce a parameter that allows them to stop sharing information. Like when you see things really look very different, then you don't want to share information. And there's all kinds of variations. Neuenschwander and others set up something that's reasonably popular in drug development for some pharmaceutical industry. They call it MAP prior. What they simply do is they set up a hierarchical model across studies. So each study becomes a submodel of a hierarchical model. If you have multiple earlier studies, then the new study just becomes the posterior predictive for yet another submodel. They call it MAP, like meta-analytic predictive. Schmiedli and other, they again allow for the case that the things are not exchangeable. I think very principled and very clean, but of course stop short of actually using the external data for a fake control arm. sorry, not fake, for a synthetic control arm. Fake in the sense not using new patients. There's many other variations. I want to talk through a few more themes in the literature there. This is Jian Chu and Yuan Qi, who have a few years ago a nice paper where they do the following thing. I like it because they use the BART. The BART is flexible Bayesian random forest model, which is one of the big success stories in Bayesian inference. It seems to work very well, good implementation, and being ultimately flexible. That solves a slightly different problem. Assume you have a current study with a treatment arm and maybe a small control arm, and you want to augment that control arm. So now the assumption is you might have 10% controls, and you want to use the external data to augment it. They are setting up a BART, like think of it as a regression tree. You're setting up one BART for the outcome for covariate X, and they're setting up another BART for the outcome. This is for outcome X under control, and this is for covariate X under control, covariate X under treatment. And the main trick that they do is for the BART under control, they add a second argument, the study indicator. What that creates is a regression tree that provides a flexible model for the outcome and explains how things might be different in the current study. And that enables them then to pull in the historical data and adjust for differences. Like, for example, in that little example here, you see down here, there's one branch where we split into S equals 0 versus S not equals 0. If S equals 0 indicates the current treatment-only cohort, S not equals 0 is the earlier ones. Then that simply says, in that part of the covariance space that you get into at this level of the tree, things look different for earlier studies and current studies. I just thought it's a clever way to proceed. Most methods that you see though in the literature that are being used, they are based in one way or another on the propensity scores. The idea of a propensity score that many of you have seen, it is a very simple one. Imagine take all the studies and just merge the data into one big merge data set, and then introduce an indicator, let's call it set. Set equal 1 for the current treatment-only cohort, and set equals 0 for the historical one. And then you try to explain for a patient in the merged population, what's the probability of that patient actually coming from the current one versus the historical one. Ideally, if the two data sets look exchangeable, that should be 50-50. It depends on the sample sizes, but ultimately they're the same 50-50. And using these propensity scores, there is now a proliferation of methods to proceed. Many of them proceed in ways similar to, many of them include a notion of taking the propensity scores just to stratify the population. That's probably a clever thing to do. And this is probably a typical example, Leo, Maxi Leo and others. They stratify the patient population by propensity score. So now they have created a clustering like on the title slide. And then in each cluster, in each stratum, in my mind, stratification and clustering is something comparable. In each stratum that they created, they just proceeded with MAP priors. MAP was one of the variations of historical data priors. A reasonable way to proceed. Chen and Wang, that's Cheng Wang, who did a lot of these synthetic control cohort strategies. They do, again, stratification by propensity score. Then after stratifying the propensity score, some of the strata, they might even entirely drop. Like if you find a stratum where you only have external data, but no data in the current treatment-only cohort, then you just drop those. There's a notion that the external data is typically more heterogeneous than the new data. For the simple reason, the external data typically comes from many different sources, so there's more heterogeneity. And then in each stratum, they proceed with, they have like two variations. It's a 2020 paper, they have another 2019 paper. In the 2020 paper, they set up, it's a non-Bayesian approach to set up, they call it historical data likelihood. They take the likelihood for the historical data with an exponent, where the exponent is based on some judgment of how similar the distribution of propensity scores is within that stratum. In the 2019 papers, they do essentially the same thing, just instead of calling it historical data likelihood, they call it power prior, but it's essentially the same thing. Yeah? One reason I'm listing that here, it's going to be one of our comparisons. It's beautifully implemented in an R package that's available and seems to work. Wang and Rosner, that's Gary Rosner at Johns Hopkins. Same game, but they actually use a multivariate propensity score. The notion being that you might have multiple totally different sources of data. I think you might have something like tumor registries, you might have observational data, you might have electronic health records, and you might have your current trial. And some of them work perfectly fine, but our drift here was we want to do something different. Basic ideas are still going to be similar. Yeah, we are going to introduce some kind of stratification. We are even going to do something that can be interpreted as propensity scores, although we shall not use the propensity scores. So at one time we'll come back to propensity scores just to point out you could report them. So our idea is even simpler. Maybe it's easiest to explain in a picture. Again, here's the current study. Sorry, now they are green patients. I think earlier it was red. Sorry to switch the color. Here's the external data. And as I already mentioned before, on the title slide, when I showed you the mixture model, I should have commented for many patients, when you have a mixture model, when you say mixture model, they hear clustering. Because when you implement inference in a mixture model, the first thing you might do is you might replace the mixture model by a hierarchical model with first an indicator, a latent indicator. The latent indicator links your patients with one of the terms in the mixture. Conditional on the indicator, you just sample from the kernel. If you interpret the indicator as a cluster membership indicator, you have now a probability model for a random partition. So I think of mixture, like many Bayesians will think of mixture models as random partitions. They think that's the same thing. Yeah, gets even worse. So we have the mixture model on the current patients. We have the mixture model on the external data. Remember, we set it up as synchronized mixture models. So they introduce strata, they introduce a partition that is synchronized, means they are matched between the two data sources. And now we could do the obvious thing. If I just drop one of the black patients from the external data here, then in that stratum, the two populations start to look the same, right? And don't ask me what to do in that case. No, actually, in that case, we are perfect. This case is a bit more embarrassing, right? No dropping of external data will create them to be the same, but you can simply upgrade these three patients here, yeah? And you also see like the typical increased heterogeneity for the external data. You might include some strata that are not replicated in the treatment-only cohort. You simply drop those. You can already see one thing that will come back later. When we set up those synchronized mixtures, we have to be careful that clusters in the treatment-only cohort, you can only place where you have a cluster for the external data. That creates a little bit of a restriction. We'll come back to that when we get down to model details.
So the assumption the external data all got treated method A, and we can.
The assumption that they should all be under control, under standard of care.
Okay.
The truth is actually, in our case, the external data comes from historical trials. They were treated under experimental therapy at that time. Fortunately, for our purposes, all of them were flops. So we treat them as if they had all been treated under standard of care. There could be multiple treatment arms if there were like more than one experimental therapy. So important thing, those strata are matched, or the terms in the mixture are synchronized. They have the same location for their components, but they differ in the weights, and we'll come back to that. One important thing that distinguishes what's coming up from what I had on the previous slide, we work with that kind of stratification, but we don't freeze the stratification. There's no notion of step one, you estimate the clusters and freeze them. Step two, you proceed with that. We fully recognize, like, we treat that stratification as a random quantity, and we properly average over it. You can already imagine what's going to happen, yeah? Like, there's going to be a posterior simulation that includes rearranging the partition. So just to summarize that, not sure that summary is needed, but you could think of it as proceeding in the following steps. First, we fit the synchronized mixture to the red and to the blue data. Once we fit that synchronized mixture, we can either resample the blue data or fill it out, or we can introduce the weighting. Step three, at this moment, we would believe that we have equivalent patient populations. At that moment, you could prove that they are equivalent. Just use whatever is your favorite universal classifier method. And if that universal classifier produces an ROC curve as the 45-degree line, then you can declare victory. If you get an ROC curve that tells you, that means that you can still tell it two apart, then you have to try harder. So at this moment, we could treat the red and the blue population as two arms of a randomized clinical trial and proceed with a favorite method. However, once you set up the synchronized mixture model, it's a very simple additional twist, and you could actually augment the model to include the response, and then you can proceed with model-based inference, and that's actually what we shall do in a moment. And it's also by answer to Jeremy's earlier comment, up to here, everything is only going to happen on the baseline covariance. Like, the whole exercise is about making the two populations look similar. Then almost an afterthought, we're going to talk about the response, the outcome. So we need some minimal notation. I'm just going to talk now. How much time do we have? 4:25 or something like that? At one time I asked them, how much time do I have? And they told me 3 hours. I mean, careful, because for the speaker, it's super easy to go 3 hours. Time passes fast when you stand out here, but time passes awfully slow when you sit on the other side. I know that, yeah? So if they didn't mean it, then they live to regret it, yeah? So I use I to index the patients, 1 through n. We have the baseline covariates x sub I, assume there are p of them. Eventually, we'll introduce a response, y sub I. There will be a notion of clusters or partition. In my mind, clustering and partition is a synonym. I'll use C1 through CK to denote the subsets, the strata of patients, like there would then be cap K strata of the patients. The clusters shall be random, as well as the cap K is random. The number of clusters is part of the random partition. Equivalently, sometimes it will be convenient, instead of representing the partition by writing down the subsets, you can just well write down cluster membership indicators, the orange guy, S sub I. If I tell you for each patient which cluster the patient is in, that's equivalent, right? It's just sometimes an easier notation to use. I'll use rho to refer to the entire random partition. So P of rho. Oh, so importantly, the clustering is not just algorithm, it's not just algorithmic clustering and you freeze it, but it's part of my probability model. So there will be a probability measure on the unknown, probability distribution on the unknown partition. We'll formally introduce missing data. In our case, those were just markers that were not collected earlier. So O sub I, those are the covariates that are observed for the IF patient. And we are ready to actually write down the mixture model, nothing fancy happening here. This is now actually just introducing notation for the explicit notation for the mixture. This is the green mixture. Was that the one for the external data, I think? So here's the green mixture for the external data. I introduced pi sub k for the weights. Those are my kernels. Oh, one drift to the kernels. You know that by a mixture of tomatoes, you can make cucumbers. You know what I mean? Sorry, I couldn't resist it. Yeah? Do you see that I assume here that the kernels are independent de facto across the covariates? That should be very convenient in the next step, because that allows us to easily deal with missing covariates as long as they're missing at random. Assuming that the kernels are independent does not mean that the mixture distribution is independent across the coordinates, because by mixing, what did I use? By mixing tomatoes, you can create bananas.
So what's I and J and K here?
Thank you. I indexes the patients, so XI is the baseline covariance for the IF patient. K indexes the terms in the mixture, and G indexes the covariance. So this one is the sum over the K terms in the mixture, where each term in the mixture has an independent kernel, which is written as a product over the covariance. And including the convenient thing is when you assume independent kernels, if a covariate is missing for a patient number I, well, you simply drop that factor in the independent kernel. You don't have to impute the missing covariates, you simply don't use them, yeah?
So what's OI?
This is the set of observed covariates for the IF patient. Like, that simply means the kernels for patient I, we just use the factors for the covariates that happen to be observed for that patient. Thanks for keeping me honest. I hate it when speakers don't explain notation because it throws you totally off track, even if it's trivial, yeah?
Yeah, so I understand the independent kernel thing. So how strong is this assumption of missingness? I use this assumption, but I was wondering.
The assumption of missing at random or?
Missing at random given the cluster here, which I believe is which term?
Certainly an assumption, it's an assumption that we need here. In our case, it was okay because the main thing that was missing was the biomarker that was earlier not being collected, that had nothing to do with the actual patients. In some cases, it might be less innocent, yeah. Cheap, so honest answer, I really don't know. Cheap answer, clinical trials in a way they're really well-controlled experiments. So if you can trust it anywhere, they understand what is missing at random and what not in a clinical trial, it would possibly be the case. But I mean, good comment, yeah.
Is this assumption stronger than the standard missing at random assumption? Because the standard missing at random assumption is that you condition on the observed data, but here you only condition on the cluster.
I didn't mean to condition on the cluster. I just said the mechanism by which covariates do not get observed for some patients has nothing to do with the actual. Good question. I never thought carefully how we want to define it here. I actually don't know the answer to your question. Yeah, it should be independent of the outcome for sure. Yeah, lest it would be embarrassing. You think it should even be independent of the entire cluster arrangement? Doesn't really exist. It's only it's only in my mind. It's only a parameter. I don't know the answer. I would guess it's reasonably innocent. Yeah. Does somebody have a better answer?
I will view this slightly differently. I thought this is composer like. So basically, you look at the margins of whatever available data, like covariates you have, right? So, because of course you have different dimensionality across different clusters. I mean covariates, right? For the I here. So you only use the ones that are reported, right?
Yes.
So I think it's more on the line of thinking like composer, like
Peter thinks I'm okay.
yeah, I think you're okay.
Yeah.
Am I understanding why this doesn't handle any correlation between covariates?
No, because we only assume that the kernels are uncorrelated. But of course, the moment that you marginalize over the mixture, the joint distribution can be arbitrarily highly correlated.
You only have one mixture.
No, why do you say only one? There is only one mixture model. But
mixture component. If K is only one.
oh, then you would have a problem, but K is random, yeah? No, there's no assumption whatsoever of independence across covariates, yeah? The moment that you have the mixture, I mean, the mixture of the independent kernels, you can easily line up to create whatever dependence you want.
Again, conditional on the component they can have in code. Conditional on the cluster.
That's right, or I would have phrased it differently. Like if you don't allow dependence in the kernels, then you might need more components, yeah? And again, let's introduce those latent indicators in orange to represent the partition. Let me see how we do on time. What's coming up now is in a moment, I will write down the same model again in red, and we're almost done, yeah? But in between, I wanted to briefly talk you through something, and I'm wondering whether I have time for that. I think I do. So now we have when you rewrite the mixture model as a hierarchical model with those latent indicators, then on the fly you have written down you get the probability model for the orange indicators, conditional on the observed axis. Means you have written down a probability model for the random partition. Remember that the orange indicators are an alternative representation of the random partition. We have a random partition model that's indexed with covariates. So at that moment, we have a regression of the random cluster arrangement as a function of the covariates. And we actually gave that a name in some earlier work. And that can be alternatively characterized in the following way. Look again at the like this is the product over the coordinates for each patient, product of all patients in the cave cluster. And then integrating out the cluster-specific parameters. I didn't highlight that, but I used earlier, I introduced on the fly, I introduced xi for cluster-specific parameters. Think of it as a location parameter in a mixture of normals. Let's give a name to that. And we could call it like a purity function, like in hierarchical clustering, you might be used to a notion of a purity function to create clusters. We call it similarity function because the more similar the covariates in the cluster K are, the more peaked this joint distribution will be. This is simply the joint distribution of all the x's in the cave cluster. That's what you get when you integrate over the cluster parameters. If you introduce that, then you can alternatively write totally equivalently mathematically. You can alternatively write the random partition that I had on the previous slide. You can write it as a prior on the, sorry, there's like one factor that arises from the prior on the weights. I didn't talk about the prior on the weights at all, yeah? But under some restriction on how you write the prior on the weights, you can again factor that to write the prior on the partition before you see the axis, and then it just modified it prior on the weights by this similarity function, which should be such that when the axes look very similar, then the joint distribution should be very peaked. When the axes are very dispersed, the joint distribution gets much flatter, and that introduces the kind of purity function that would favor clusters with very similar covariance and penalize clusters with very diverse covariance. End of the footnote. This was just a footnote about the introduced random partition here. We don't need that again, yeah? So let's go back to our random partition. This is just repeating what I had on the previous slide, just I put now explicit blue super indices to indicate it's for the external data. And then just do the same thing again for the current treatment only cohort. Writing down all the same things now with a red superscript, except for one thing, as many times in life, what you have to pay attention to is what you do not see. There's no super index on the cluster parameters. Intentionally, of course, because that creates the synchronized mixtures, yeah? So at this moment, we have the common atoms mixture model for the two populations. Back to the next slide. One more restriction that we want to introduce. It's not strictly needed, but for the story as I told it so far, I would have to insist on the size of the red clusters being less than or equal to the cardinality of the matched blue clusters, lest you cannot thin one out to create it, to make it look like the other one. At this moment we have a probability model to do our thinning out. And we could in principle do the thinning out or reweighting. I think it should be plausible from the previous picture where I just showed you again the synchronized mixtures. Is it plausible that you should just take the ratio of the weights to do the reweighting? And in fact, that is correct. You should use the ratio of the weights for the reweighting, making that a little bit more formal. What we want is we want to be able to use posterior Monte Carlo averages conditional on the blue patients to approximate posterior expectations for the red patients. That's just my definition of the correct reweighting, yeah? Where I can use these weights up there, the ratios of the weights. One more little thing. Whenever you see weights in the denominator, you should become a little nervous because the weights could be really small, right? But at this moment, you can now Blackwellize, like replace the unknown weights by a conditional posterior mean, which could essentially be the cardinality of the blue cluster. Sorry, the relative size of the blue cluster. Use that as an estimate for the blue weight. The advantage being the size of the blue cluster must at least be 1, so it cannot go to 0, yeah? I will leave it at that. With that comment, it's relatively easy to show that these weights achieve exactly this desired requirement, yeah? That's the formal argument for showing that the ratio of the pies is the correct weight. And I skipped this argument, it's not exactly long. For those of you who still remember days before MCMC, before we used to do MCMC, there was something called importance sampling. Jerry, how can you not?
We learned it.
You were not even in grade school doing it.
We learned it in 615.
Importance sampling used to be the standard method to implement Bayesian inference. It died overnight when MCMC came about. One of the reasons being importance sampling is very easy, but the big problem is it was impossible to bound the weights because the weights are essentially the ratios of the important, the correct weight is the ratio of the target distribution over the importance sampling distribution, and especially in multivariate problems, that is impossible to control. It can get out of hands, yeah. Which created funny situations. But yeah.
So we compare these two data, you have different custom label, right? So how you map one label here to another custom label?
If you were to set up 2 separate partitions, you would be hit with all kinds of label switching problems. The way how we wrote it down, the terms in the mixtures were actually they were matched. Okay. So quick answer by notation, like by setting it up.
So but you need to order them first.
No, we created choice. They are created as strings on the clusters. I mean, it's a good instinct to watch out for label switching. Yeah, like essentially you're concerned about label switching. How do you match them? Yeah. since they are created, they're created jointly. When I create them, I call that they start a cluster sampling.
You do joint?
Yes.
I see. I thought you do separate.
No, good point. That would be a hopeless undertaking. At this moment, we actually have created importance sampling setup because we are using the blue density to estimate averages with respect to the red density. Do you realize we did not need the ratios of the densities, we only needed the ratios of the weights. It doesn't matter, the dimension of the densities don't matter, yeah? So this is important, density-free importance sampling, end of that footnote. Let's skip that one. I already talked you through it quickly. Did you notice so far I didn't mention outcomes, yeah? But now we are done with setting up the synchronized mixtures. We know the weights that we need to adjust them or to reweight or to thin out. In principle, we could now do the thinning out and proceed as if it were a randomized clinical trial. We might just as well to augment our synchronized mixture model with one more submodel to get a model for the outcomes. And all what we do here is, since we already introduced the clustering, we introduce now for each cluster a cluster-specific parameter to index the sampling model, or to index a red sampling model for the treatment cohort. And of course, the same thing to index a blue sampling model for the matched control cohort, for the matched control stratum. And at this moment, we have actually a model for the outcomes. Can I still sneak in a 1 minute comment at this moment? At this moment, we have actually a flexible regression model for the outcome of the covariates, which allows you a regression on a variable dimension covariate vector. It always kind of tickled me pink to notice like regression is one of the basic problems that we can do as statisticians. But doing a regression with a variable dimension covariate vector, there's no canonical solution. I mean, there's all kinds of workarounds, but really no canonical solution. Like in principle, obviously, when you teach stat 101, you always assume that you have the full covariate vector for everyone. If you don't, then you have to impute it or do some fancy dancing. This creates actually an approach to do regression with a variable dimension covariate vector without imputing missing data. And I thought it's a nice story, end of that footnote. So at this moment, we have a model for the outcome. So we could now start to consider inference for a treatment effect. What we would simply do is let's assume for a moment that the interpretation of the parameters that index the sampling model could just be something like mean event time. Sadly, in the glioblastoma example, the outcome is overall survival, sadly, because it happens soon enough that you can actually use that as an outcome. So just setting up an exponential model with mean theta k. I think that's all what we did actually, yeah. Then the effect in cluster K could just be the difference of the mean outcomes. And then as the reported treatment effect, it just take the red weighted average of the cluster specific treatment effects. So now we have a treatment effect. And actually, funnily enough, there's a nice interpretation once you have that mixture model set up. There's a nice interpretation in terms of propensity scores. So let's again do the exercise of merging the data sets and create one merged data set. And again, latent indicator that tells for every unit in the merged data set whether that patient really came originally, whether the patient was originally a red patient or a blue patient. Then you can argue that the ratio of these are not exactly the propensity scores. The ratio of propensity scores for covariates close to one of the cluster centers is exactly the ratio of the weights, which is kind of nifty. So that synchronized mixture model actually includes an easy expression for propensity scores, propensity odds, but it obviously implies the propensity scores. But we don't use these propensity scores, but you can get them if you need. I was going to tell you about two simulations. I prepared to talk about two simulations. Maybe I'll just do one, and that's maybe a good place to stop them. So back to the application, the GBM trials in MD Anderson neuro-oncology. We have some 340 patients, historical patients, 11 covariates. There seems to be kind of a consensus what are the important covariates in glioblastoma. Now after these 340 historical patients, we have a new single-arm trial with another 49 patients. And we want to use the blue historical data to set up a synthetic control. And we shall do that now in a small simulation, and let's see how it works out. Two simulations. We want to set up that synthetic control to compare the new experimental therapy with standard of care, formally carrying out the comparison of the two hypotheses. They say for a treatment to be of interest, they want to see a hazard ratio of 0.6, struck me as being a bit a steep requirement, but that's what they tell us. So the new treatment is victory when the hazard ratio is less than 0.6, and it's failure when the hazard ratio is above 0.6. So those are the two hypotheses we want to focus on. And now here are two simulations, like we actually simulate possible outcomes. On the one simulation, we simulated under the null hypothesis, means we simulated outcomes for the new patients that were no different from the historical patients. Using now the historical data and adjust it, going through all the steps that I talked you through. In the end, this is the survival curve that you see, and doesn't matter what kind of method you use, there's obviously no treatment effect. And actually, formally, within the model, we find the posterior probability of the alternative is less than 30%. No matter how you want to proceed, that surely does not justify reporting the alternative. Here's another one. When we simulated under the truth with a hazard ratio of less than 0.6, after going through the adjustment of the two populations, we ended with two survival curves like this. And if you're just looking at the picture, I would say there's clear evidence for a treatment effect, and sure enough, we get 80% chance of a treatment effect. That, of course, was just a single simulation. We carried out a larger scale simulation. I'm happy to talk you through it. Maybe I'll just show you one picture. So there were three big scenarios that we used. In one scenario, we simulated, we call it the oracle scenario. We simulated essentially using a model that's underlying propensities, that the use of propensity scores. So in this case, that should really favor the use of propensity scores. The other two scenarios were implicitly using propensity scores that did not use the assumed model. Oh, when you use propensity score-based methods, you need to estimate the propensity scores. Usually stupid logistic regression, yeah? So in the first case, sorry, there's nothing stupid about logistic regression. Simple logistic regression, yeah? In the first case, the logistic regression was actually what we used for the simulation. In real life, the assumed model is, of course, never correct, yeah? Like double robust methods are really double unrobust because the propensity score model is never correct, the outcome model is never correct, so usually both of them are wrong, yeah? And you'll see in scenario 2 and 3 what happens when both of them are wrong. On the vertical axis are biases, so 0 is good, yeah? On the horizontal axis, different levels of the true treatment effect in the simulation truth. And the different color box plots show different methods. The reddish color are propensity score-based methods. The blue kind of colors, they are based on that synchronized mixture model. And this is under the oracle scenario when we actually simulated essentially when the simulation truth was matching the assumed model for the propensity scores. And essentially the main message to take home here is everything is kind of okay. Like everyone is kind of around 0 as it should be. But lo and behold, when you change the simulation proof, wait a minute, did I promise you? It's exactly the other way around. Reddish is the red colors. That was backfiring now. The red colors are the synchronized mixture model. The blue colors are the propensity score model, the propensity score approaches. And now you can already see how when both models are wrong, then obviously all bets are off of propensity scores, and sure enough, you get to see that. There was one more comparison that we carried out that is not shown here. One method that is very nicely implemented, and I forget the right reference, if somebody knows it, please tell for proper credit. Just using matches, just stupid matches, like for each patient in your treatment arm, try to find a patient in the control data that kind of matches that, which is typically the kind of scheme that's underlying the various computational health approaches of our machine learning colleagues. It's actually not stupid, it works very well, yeah?
Integer optimization.
Sorry?
Maybe it's integer optimization.
Integer optimization?
You use the integer program to try to find a match.
Oh, okay, so the optimization to find the optimal match might be delicate, but it doesn't have to be the global optimal one. As long as it's a good one, it's good enough. But that said, yeah, it boils down to a computing problem then. That's actually all I wanted to tell you. So in the end, I tried to talk you through a model-based framework to create the synchronized mixtures. And I mean, even if you ignore all the details, once you set up synchronized mixtures, I think it's plausible that at that moment you can adjust for differences in the population, yeah? And that's exactly what I tried to talk you through. There's obvious limitations. One big limitation is, in this particular application in neuro-oncology, there was a consensus set of 10 covariates to look at. In many other applications, you might have a huge candidate subset of baseline covariates, especially the moment that you add biomarkers and genomic covariates, all hell breaks loose. Then this will not work anymore because Jeremy and me, we are in the same cluster in terms of our preference, maybe, in terms of some of our preferences for statistical inference. God knows what your music tastes are, yeah? So if you add sufficiently many covariates, sooner or later, everyone looks different, yeah? So if you have like huge covariate vectors, you cannot play that game, then you have to include some notion of dimension reduction. And there's various ways of doing that, and many of you might know better than me how to do that. That's all I wanted to tell you today. Thank you, yeah?
Can I start? This is a naive question, but you keep referring to it as a synchronized mixture. Based on the model, it looks like you're just combining the samples and clustering all of them together. The only difference is that you have this restriction that you cannot have a cluster that only have the treatment on it, which I have a follow-up question on that. But is that understanding correct? You're just
Yes,
combining.
totally correct. Totally correct. The only addition, the only comment I would make to it. So did everybody understand? Irena's comment is, you don't really need to do any fancy dancing, just throw everything together into one merged data set, cluster the merged data set, then automatically, when you take it apart again, it automatically produce two synchronized partitions.
Yeah.
The restriction though that you recognize would be awful, because you would have to carry out the clustering of the merged data set, restricting to no cluster including only red patients.
So this is a follow-up question. Why do you have that restriction? Because in theory, you can have someone in the treatment arm for which you do not have a much historical control. And if you do recognize that, is that a bad thing?
No and yes. Since I set up my model with the restriction, I never had it.
Well, yes, obviously.
That's why I said no, yeah? Like, it's a restriction of the model. I mean,
Right.
when you fit a straight line, then you'll always see a straight line, yeah?
But clinically, like.
Oh, clinically it's possible. And it's a super bad thing. That's why I said no and yes, yeah? If your current patient cohort, if you suddenly see like, if there are suddenly like extraterrestrials recruiting for your patient, for your a new study, there is no way on earth that you can adjust the historical data to match those extraterrestrial patients. You just can't do it. You can't make inference.
Yeah, but I wonder if you're missing some of them because we cover history.
I not see it. So I get answers, I will not see it, whether it's valid or not, that's a different question, right? And my answer would be no, it's not like, if you really have patients in your new treatment only cohort that look nothing like any of the historical data, as long as they look somehow, as long as the new patient population looks approximately like the old patient populations, I'm okay. And here's the good news. Things are always approximately the same. No, it's, of course, the inference will only be good to the extent to which the approximation is good.
I was wondering how much faster it would be if you remove that history.
Oh, it means then it's super easy, yeah? Then you pay me. You totally could. But I mean, if you want to actually include the restriction, then it would be super awkward, yeah? Like, I mean, doing the synchronized mixture is not exactly difficult either. I mean, we do the same kind of MCMC thing, yeah? But already building the restriction in, then you don't have to check it. So cheap, quick answer to your double comment. Building the restriction into the posterior simulation is just much easier than trying to impose it afterwards somehow.
Thank you.
We saw this nice cartoon, which looks nice, but I wonder what the real data look like, because usually they have a big continuum, and if you break down into too many clusters, then each one has very small sample size. If you just have a few clusters, then they are very diverse, right? So what does the real data look like?
Yeah, sure. My model is correct, the data is wrong. No, good comment. Honest answer, I actually don't know. Longer answer, the real data is categorical. So that cartoon would just be in between on the latent probit scores. But it's actually an interesting thing because, like, for clinicians, it would actually be interesting to know how the populations are different. Yeah, something you might want to report. Your other comment that you essentially articulated preferences on the nature of the partition that are totally meaningful, like clinically and in terms of interpretation. One of my favorite themes. When you want to do clustering or when you want to report inference on random partitions, maybe you should really maybe one attractive way of phrasing it is as a decision problem, because you typically have, like in this case, we didn't really try to interpret the clusters, but if you want to interpret them as meaningful patient subpopulations, they probably want to be significant, want them to be interpretably different. You don't want to have clusters of singletons because they're kind of meaningless. So I mean, honest answer, no, I have no clue what it really looks like, and I don't quite know what to do then. But I think it's a good comment, and it's actually something that we are trying to explore at the moment. Yeah?
So I think if I understand your method correctly, is basically you want to do this sort of subgroup matching in the analysis rather than one-to-one matching, because you want to utilize potential underlying homogeneity across different subgroups that between the treatment group and the sort of the historical controls together. So I wonder that what if you, I mean, the question related to this question, what if you reduce the sort of the size of clusters? Because in principle, I can use this propensity-based, the score-based matching to a one-to-one match. But of course, I will lose this sort of possible homogeneity among some of the patients in these two groups. I wonder how sensitive or what's the power of your method, in other words, that this group-based matching will gain out of the one-to-one matching.
First of all, I appreciate the comment that you could call it as a generalized matching method, because instead of matching individual patients, we match clusters and all it. Because the matching approach seems to really be competitive, so it's always good to pick it feedback on a winner. There is an obvious trade-off of choosing of having large clusters versus like, on one hand, you want to have homogeneous clusters, on the other hand, you might want to have large clusters. We didn't explore it at all. We had actually, I mean, here's the truth. We actually set up vanilla digital process clustering, like the Chinese restaurant process, without any much fancy dancing. There's an obvious trade-off. There might be something like an optimal cluster size. We didn't explore any of that at all. One could potentially, like maybe before I try to look for an optimal cluster size, I would then rather replace the Chinese restaurant process that is notorious for creating small clusters. I will replace it by something where you have more control a priori on the cluster sizes, which is a popular game in non-parametric ways. But we haven't yet at all been down to finding optimal cluster sizes. I don't quite know the answer there, but I like the thought of thinking of it as a generalized mention.
Data is common. You do important sampling or density ratio in each cluster, right? What the other way you could do is if you just use a mixture density, take an important sampling altogether.
Then you have.
Yeah, I know you can lose efficiency. The reason you can gain efficiency is this kind of group margin, the treatment effects tend to be different. The if treatment are different, this kind of stratified margin is more efficient. But one question you have is the strategy you create, the mixture you create is unsupervised variable. It doesn't imply treatment effect of different between this strategy. So I think that's better way you should have some supervised version to identify the strategy or mixture.
When you say supervised,
Which use outcome.
oh, we use the outcome, like it's all, I should have,
No,
so not supervised is.
By we create mixture, you don't use outcome. You just do mixture.
Oh, there was just the sequence in which I introduced it. In the end, when we set up posterior inference, we set up posterior inference in the big model, including the outcome.
Right, but the mixture you identified doesn't use outcome. You only use X. You only use the correlates.
Well, it won't be down the first time, but when we actually implement inference, it includes a factor in the joint likelihood for the outcomes. For better or for worse, the good patterns in the trouble where they actually use the propensity score, but we don't use them for inference, yeah. But so no, we actually use the outcomes in the. They probably don't change the mixture model much because when you have 11 covariates and one outcome, it probably doesn't drive them. It probably doesn't drive the partition, but it's actually in there. But it's not supervised in the sense that we don't even use informative trials on how the patient should be clustered, let alone known labels, yeah. Like using important sampling with densities like on high dimensional density, like I think beyond like 4 or 5 dimensions, it breaks down.
Another question.
So I was wondering, like, because I noticed that both sides in your historical data and your single arm trial data are like both pretty small. I was wondering, and also the number of covariates not large by and so I was wondering, like, how uncertain the cluster is, how many clusters did you actually identify those?
The sample size in the current treatment only study being small, that's just that's typical. Like we're talking about early phase studies, you won't have big sample sizes. The external data, of course, could be much larger. Yeah, like in this case, deliberately they cut off. I think we only took like historical data, historical trials a few years back. When you go too far back, you would get you would risk all kinds of problems. If you were to use different alternative data sources, it could be much larger and would still work. It would work probably in computation, it would probably work like up to 1,000 or so for the external data. Much more than that, then I would really suggest machine learning approaches like matching methods would probably work quite well. You had another comment.
Yeah, I was wondering, like, how many clusters?
Oh, how many clusters you find? I don't know off the top of my head, I can easily find out, educated guess, 7-ish. Basically just an educated guess, I don't remember for sure now. Probably more than what you would think, yeah? Because we use the stupid heuristic process bias that tends to a priori favor small clusters too, yeah? But something like, I guess in single digits, I don't remember it now, because we never focused on the partition, yeah? Because there was nothing trend about it.
It's random.
It's random. But like, I think you asked like, what's the number, what's the kind of, what number do we estimate? Somewhere around 7-ish, I would guess, yeah. But good, I mean, good drift, like, you might actually want to report inference on the partition, because by itself might be of interest clinically, yeah. It included it all, yeah.
Let's thank our speaker.
I think there's one more comment. Pick it up.
I'm just asking, like, when you're choosing the external data, like, have you considered, like, why you choose, like, historical? I know it's easier to find the same variables and same, like same population. But have you ever considered, like, using, for example, other survey data that in this case?
Quick answer, not survey data, but like other studies we could in principle use. We are trying to currently work on that. The truth is, and many of you might know that, it's amazingly difficult to convince investigators to share their data. We finally got, some of you might know the INSIGHT trial. We finally got now data from the INSIGHT trial, which also includes a treatment cohort actually, yeah. So control data is usually easier to get. So we have control data from 2 other studies now, and more from the INSIGHT data. That's certainly very useful, of course, when you use other studies from other investigators and other hospitals, etc. You of course increase the heterogeneity. If you look at longer lists of covariates, like one important thing is of course garbage in, garbage out. You have to be very careful that all the variables are defined the same way. Like as long as it was coming from the same group of clinicians, we could trust that the variables are throughout defined the same way. You have to make sure that they define it, that they code everything the same way, lest you get nonsense. So it gets much more difficult, practically, the logistics, mathematically, of course, totally legitimate. Very good.
All right. Thank you.